this very relation. Okay, so this is the time. That's it for a moving clock. And this is the coordinate time. Let me explain it again. Because most of the confusions arise because of this very relation. Yeah. Just this. I am feeling actually cold. Okay, 2 ACs are functioning. Okay, you can carry it on. 2 ACs are functioning in the room. Okay. Yes. Okay, so what does it mean? You carry a clock. Let's say a person carries a clock with him and it reads some time. Clear? For that person, this time is always there. It will read how the clock functions. Clear? It will read as a normal clock. There will be no change. Now another person sits, looks at that very clock. Clear? And measures that time. It means this delta t is the time measured for the same clock. I mean this moving clock. In other words, you are having a clock, okay? It's moving, and you are here a stationary observer, okay? At rest, let's say you are looking at this very clock. Clear? This clock will appear for you to tick slow. I mean to show. The duration of time what you are measuring, it will appear. It will get elongated. Clear? In other words, you will see that clock moves slower for you. That is what this time means. This delta t is the time what you measure for that moving clock. Got it? So in that sense, we call this as a coordinate time. And this delta t prime is a time which is shown by the clock itself in its own frame of reference. Got it? So you can think in other words, okay, let's say for the moving observer, so you can think it in the other way around. For the moving observer, the clock which is at rest, clear? So you should have the same effect. Samajh aaya? In that very case, the moving observer will have a coordinate time, and the time what he measures for the other observer will be this thing. Samajh aaya? Let's say if you are having the other way around, it will be like this thing. This delta t prime will be gamma delta t. Samajh aaya? So it's purely relative. I mean, it is purely reciprocal. I mean, if you are watching a moving observer, his clock for you will appear slower. Clear? But if that observer is watching your clock, for him, my clock will be slower. Got it? So it is completely reciprocal. It is simply it gives us actually a notion of a coordinate transformation. It's a purely coordinate effect. We will see when we try to figure out what are the relations between the different coordinates. You will see actually this kind of relation exists. It gives us actually the relation between the time coordinates. Time measured, the proper time and the coordinate time. Got it? Samajh aaya? So it's not like that you see the clock automatically, let's say it slows down, and for you it does not slow down. Okay, so that will come. So that will arise only when we will have some acceleration, some constant acceleration. Clear? So where this reciprocalness breaks down, this symmetry breaks down. So that gives rise to what you call the Tune paradox. Samajh aaya? So that I will take in detail in the next lecture. Samajh aaya? Clear? Have you got this relation? Okay, so this is what we are trying to do today. This object always remains invariant quantity. This proper time for a given clock is always same. Okay, for an observer, let's say I am moving, for me, my time is always there. It neither slows, it is same thing what the clock reads. Okay, it does not change. But it is only for an observer who is watching my clock. Got it? Okay? Any confusion? Further confusion? If you have any more questions, just tell me. Because most of the paradoxes arise from this very relation. Okay? Or the length contraction. So they are related, these two things. So if you have any more confusion or any other confusion, any question, just tell me.
So that means delta t is also invariant in its
No,
own
no, no.
frame.
Delta t is not invariant quantity.
In its own
it's
frame
a
of
no, no.
reference.
It's a coordinate time. It's something you measure that moving clock. It is a time when you look at the clock. So that moving clock. It's not an invariant quantity. But okay, so but for in the other way around, let's say if I am moving, but with respect to me, the stationary observer is moving. The other observer is moving. Okay, I am moving with respect to one observer, and that observer is moving with respect to me. Clear? For in that very sense, you have to take this kind of relation. So this delta t prime will be now the coordinate time, and this delta t will be what? The proper time. समझ आओ? Okay, coordinate time is not an invariant quantity. Only the proper time is an invariant quantity. We'll see it in a moment. Clear? It is completely reciprocal. The way you think, let's say, okay, so let me put this paradox this way. I mean, you say you are having two twins. Okay, you send one at some speed, let's say half the speed of light, for a journey. Okay, and once it returns back, you see the moving, the person who has set up in a journey, he looks, younger, or rather, he turns out to be younger than the person who is stationary. Clear? You can think the other way around. For the person who is moving, who has gone for the journey, the other person is actually moving. Clear? So you can think of a reciprocal effect, but here it does not work. In this kind of what we call as a twin paradox, it does not work. The reciprocal effect does not work. Okay? The symmetry is broken. This I will tell in detail in the next lecture. Got it? Okay. So, okay. Now let's look at, okay. So let's think of a curve in ordinary, Euclidean space. Okay. Let's think of a function. Okay. So let me write a function y is equal to f of x. Here is another better way to write this kind of function in terms of a parametric form. Clear? So you can think, okay, so if you write let's say any kind of curve, any kind of function, okay, instead of writing it in this fashion, okay, you write it in terms of, you introduce a parameter for that. Okay, let me give you an example what I mean by that. Think of a circle. So you are having x square plus y square is equal to a square. Let's say a is the radius of the circle. Clear? So this is the equation of the circle. It's where it defines very well the circle. Instead of writing the equation of the circle in this fashion, I introduce a parameter which takes certain values, set of continuous values, from let's say one value to the another upper value in a continuous fashion, and write this equation in a parametric form like this thing. So you write it like, okay, x is equal to a cosine of theta, y is equal to a sine of theta. What is the parameter here?
Theta.
It is the theta. Okay, and theta changed from, let's say, 0 to 2 pi. Clear? So here what you have introduced? A parameter theta. Clear? And it takes all the values, and this parameter actually characterizes your trajectory. So this kind of this kind of curve is parameterized by the theta. So let's now go to the let's go to the four-dimensional space-time. Okay, this will be very general in nature. Let me consider any kind of trajectory. Okay, or instead of, let me consider any sequence of events. First, let's consider any sequence of the events. That sequence of events I will always represent by a curve. You can think, let's say, okay, so this is, let's say, the x, and this is the time. Clear? So let me take the sequence of the events. that means, so you are having one event here, another going like this thing, whatsoever. Okay, so all this sequence of the events, you express this by, let's say, a kind of curve. Got it? And this curve is parameterized by some parameter. Samajh? So you take the sequence of the events, okay, and that is represented by a parameterized curve. Okay, and an event, let me describe an event by some x. X represents the coordinate, clear? And let's define the parameter lambda. Okay, we will see how we can choose the lambda. Lambda can be any arbitrary parameter. Now I can change the parameter. I can actually arrive at, with the help of the values of the lambda, I can arrive at this very curve. Got it? Samajh? So any curve that is parameterized by certain parameter, okay, and okay, so that represents always a sequence of the events. Now, if you are having a particle that traces out a trajectory, out of all these kinds of curves, which is very important for us, is a trajectory of the particle, which really represents the trajectory of the particle, and that curve we call as a whirl line. So you can be having all the possible events, and you join those events by a parameterized curve, or you represent those events by a parameterized curve. Out of all those possible curves, okay, you will be having only one curve that represents what? The trajectory of a particle. Clear? And those trajectories we call the whirl lines of the particles. Samajh? Okay, so now let's try to figure out what is the arc length of this very curve. Because ultimately, when you define a curve, you should know the arc length of that very curve. Arc length means the separation between the two intervals. Sorry, the separation between two events. So if I take any 2 points, let's say you are having an event happening at point P and another event, let's say, which is very close to this P. So let's call that event as Q. Now let's calculate this length between P and Q. So this can be in general a curve. That's why we call it as an arc length. Okay, it is not necessarily to be a straight line. It can be anything. We need to figure out what is the arc length here. Got it? How to define it? Okay, so we have this very quantity. Okay, since I am taking only the two coordinates here, x and t, so I will write like this thing. ds square is equal to minus c square dt square plus dx square. Clear? So now let me define the arc length. Okay, arc length I will write, let's say, some pq, and you integrate from where? This p to an invariant arc length, I should say, and this length should be invariant under a given transformation. So under a given coordinate transformation. This is very important. When you define the length of a vector, that length should remain what? Invariant under a transformation. Clear? So similarly, I am defining an arc length which is an invariant quantity. Clear? So how I define it? So if I can define it from this very object, from this ds. So you do it like this thing. Integration over ds. What ds gives me? ds gives me actually the length of the interval between the events p and q, if they are infinitesimally close to each other. Got it? Okay. So now what it will be? So it will be some p to q. Okay. So you can write it in this way. Okay. So I'll write, because so here I will define it in this fashion. Since this curve is parameterized by the lambda, okay, instead of some proper time or so on, so I will define this length in terms of this lambda. Clear? So it will be something, okay. So let me write this proper length. Okay, so let me write it like this: ds by d lambda kind of thing, and d lambda. Can I write it? Can I write it?
Yes, sir.
Okay. So now tell me what is ds by d lambda. So it is something. Okay, let me write some lambda 1 and lambda 2. Lambda 1 is the value of the parameter at point P, and lambda 2 is the value of the parameter at point Q. Okay? So it will be something like, okay, dx by d lambda whole square minus 1 by c square dt by d lambda whole square, and here is a power. Okay, clear? So ds by d lambda I am taking it. So you take ds by d lambda, since there is a root, you take then d lambda inside, that will be a square. Clear? Any problem? Okay. Now this defines your what? Arc length. So is this an invariant quantity? Now we need to check if I make an arbitrary coordinate transformation. Okay, let's take an arbitrary coordinate transformation from some lambda to lambda prime is equal to f of lambda. Okay, like you are having x prime goes to s f of x, and this is a coordinate transformation I am doing. Okay, changing the parameter from one coordinate system to the another coordinate system, you change actually the parameter. Clear? Okay, so now let's look at under this kind of transformation whether this is really invariant or not. What does that mean? The form of this length should be same. Okay, or the form of this very integral should be the same. Got it? Any problem? Okay, so let's try it. Yes? Okay, so let me write then in the primed frame of reference. So you take from point P to Q. So let me write it in the primed frame like this thing. dx by d lambda prime whole square. So I am defining it in the primed frame, and we will show this is actually same as in the unprimed frame. Clear? Raise for half. समझ आओ? So now let me take the coordinate transformation. This is complete and arbitrary coordinate transformation. Okay? So whether it is linear or non-linear whatsoever. So this is an this defines any transformation. Okay? So you are having of P to Q. So I will write is d lambda prime. Okay? So let me use a chain rule here. So it will be something dx by d lambda and then d lambda by d lambda prime. Can I do it? Okay, whole square minus 1 by c square dt by d lambda and d lambda by, sorry, so this is a prime, d lambda by d lambda prime whole square raised power 5. Now you can take out of both the terms this d lambda by d lambda prime out. Can you take it? So there is a root sitting here. Okay, so this is a square quantity. When you take this out, so square and root cancels. Clear? So what remains there? So it is P to Q d lambda prime. Then you are having d lambda by d lambda prime, and you are having this dx by d lambda 1 by c square dt by d lambda whole square. Clear? Raised power half. So what it is? So this and this cancel. So you are having d lambda kind of thing. Okay. So in other words, this is same as d lambda. So you see the form remains same. So it means we have defined successfully the invariant arc length. Got it? That trajectory or that curve is specified by some parameter lambda. Clear? Okay. So if you have any question here, just tell me. Now let's give a physical significance to this parameter. Okay?
So arc length intervals.
Length between the intervals.
Arc length and interval difference. What's the difference between arc length?
Interval will usually defined by ds square. Okay? Got it? So we have shown in the previous lecture ds square is an invariant quantity. Is that true? So the interval is an this thing, or the length square, I should say, that is an invariant quantity. Now what I have shown? Arc length. Okay? Not the square of the length, but the length itself. So this will help you to understand how to define the length of a curve. Okay? So that means you need to take all the values from P to Q. Got it? Okay. Now let's try to interpret or let's give the physical significance to this parameter lambda, okay, in special theory of relativity. Okay. Okay, so let's consider two frames of reference. You are having some k prime, okay. So I am considering the two frames of references. Okay, let's call one frame as to be k prime, which is attached to a, okay, this k prime is attached to a clock, and that clock traverses a trajectory. It's worldwide. Clear? So that means I am saying, let's have this x and this t. So this is now the world line. Okay. So let me consider this to be the world line of the particle, and it is associated with a clock. Okay. And I will call this as the k prime frame. So that means, so I am having a clock here. It is moving. I mean this k prime. So you can call this as k prime frame of reference. So in this frame of reference, our clock is at rest. Is it? Because it is attached to this frame of reference, and it's rest in its own frame. Okay? And what it will show? It will show the proper time. Got it? Okay. So in this frame of reference, I can say this dx prime is actually 0. Because it's at rest. There is no motion. Huh? So, and what it will show, this dt prime, it will show as the proper time. Tau. The time that is shown by this clock, okay? So that will be simply what? The proper time. Samajh? Okay. So now let's move. Okay. So let's consider the another frame of reference, k. Okay. So that will be simply an observer sitting outside of this very clock. Samajh? Or a person sitting at rest watching that clock. Okay. So we call that as the k frame. In the k frame, what you will measure? You will measure the time of that moving clock. Okay. So let's call that time to be dt. Okay. And since for me, the observer sitting outside, this clock is moving, clear? And this delta x will not be equal to 0. So in other words, they will simply specify me the coordinates of the clock. So this will give me the coordinate time, okay, and this will give me the position of the clock. So clear? Okay, so now by invariance of the interval, so we have shown this thing, d square equal to minus c square dt square, okay, plus dx square. So that is same as what? C square dt prime square dx prime square. I am considering only two coordinates, x and y. Those we can attach. Since I am considering motion only along the x direction, not along the arbitrary direction. Okay, so this is your k prime frame, and this is what? K frame. Okay, so now what we have? This object is 0. Clear? So this is the invariance of the intervals we have shown already. Okay, so or I can write like this thing: dx square is equal to minus c square dt square plus dx square is equal to minus c square tau square. Clear? Because tau is now our proper time. Okay, so what you will get this tau? Now let's look at, okay, so you can call this as d tau for the time being. Let's write this as d tau. Okay, because we are looking at the events which are infinitesimally close to each other. Got it? So let's write this as d tau square. So what you get? So you are having this d tau as, anybody? So minus ds square by c square raised power half. Is it? So forget about this very equation. So minus c square, okay, so minus will come here, 1 by c square ds square half. So how much is that equal to? Now let's look at here. So this c square will divide this thing. Okay, so you take this dt out. So it will be something root of 1 minus dx by dt whole square. Okay? Clear? Okay. So now, so or I can write this d tau to be equal to dt root of 1 minus v square. Sorry, there is a 1 by c. because we have taken c square common. Huh? This cancels with this thing, you have to divide it here. Clear? Samajh? So now tell me what is the amount of time that is shown on this very clock. So if it moves from P to Q, let's say some P to Q, clear? So what is the amount of time shown by that very clock? So you need to integrate this very equation. So it means the proper time shown by the clock, so it is like this, dt root of, so this is simply the time dilation. Huh? Clear? So, so what you are having now? The proper time. Clear? So now let's look at this very formula. ds square is an invariant quantity. Clear? And root of ds will give you what? Root of ds square. It is simply the arc length. So we have just shown the arc length is what? An invariant quantity. Clear? So it means what this proper time is? An invariant quantity. So in other words, I can say my proper time, I can write this as something magnitude of ds by c. Okay? So why magnitude? Because for different kinds of intervals, ds square, for time like intervals, ds square is less than 0. For space like intervals, ds square is greater than 0, and now it is 0. Clear? So I can define now my proper time to be the length of the interval divided by the velocity of light. Samajh? So it means now what should be a suitable parameter that will specify my trajectory? So it should be a proper time, because we have shown when I have chosen a parameter lambda which characterizes your trajectory or which characterizes your curve in your this four-dimensional space-time. Okay, and we have shown the arc length is invariant. Got it? So now I am looking at a kind of physical interpretation of that parameter, or how I can choose that kind of parameter. Clear? So a suitable parameter to characterize the word line of the particle should be what? The proper time. Okay, because it is an invariant quantity. It does not depend on the frame of reference. Invariant quantity means it is frame independent. If you are having a variant quantity that varies from coordinate to coordinate, it means it's a coordinate dependent quantity. Okay, when you parameterize a given curve, okay, the parameter should be frame independent. It should not depend on what? The frame of reference. Samajh? Clear? Okay, so have you got now? So any word line now we can always parameterize by the proper time. So that means I can write now the word line of this very particle, something, let's say x of tau. Any event on this word line, okay, will be specified by the coordinate x and parameterized by the tau. And this tau will be given always by the clock attached to that very observer. Clear? If you have any question, just tell me. Okay. Okay, so now let's try to figure out the relation between the coordinates. Let's try to figure out the coordinate transformation between two observers. Okay, how to specify that? We will do it in a very general way. Then we will figure out from that generalization the Lorentz transformation, what we know, the Lorentz boosts. Clear? So let's figure out the coordinate transformation. Okay. Okay. So the way we'll be doing, so it adopts both accelerating frames as well as inertial. You should remember one thing: special theory of relativity is not applicable to inertial frames. It's applicable to what? Accelerating frames as well. Samajh? So you can apply the relativity I mean, it handles both kinds of frames of reference. Okay, so we'll be doing, let's say you are having an observer that's moving along some trajectory. Clear? Okay, so instead of, let's say, this kind of non-uniform motion, let's consider an observer, okay, which is moving with some velocity. Clear? Okay, uniformly. So let me write this as a uniform motion. Clear? An observer A, and this observer A wants to assign the coordinates of some event P. Let's say P is an event. Clear? How it can do it? This is how we can figure out the transformation between the coordinates. Suppose you are two observers are there, observer 1 and observer 2, and observer 1 is moving. Clear? And this observer, moving observer, wants to assign the coordinates of the event of the observer 1, rather observer 2. Clear? How she can do it? Can anybody give me an idea how she can do? I mean, suppose you are having observer A, it's moving with some uniform velocity, let's say, and this observer wants to assign the coordinates of some event P. Or you can call this as an observer, another observer. Clear? So, समझ how this person can assign coordinates to this point P? Suppose one might button. You should both of. Okay, so you are watching this both of, huh? Right? So क्या पट करने में coordinates assign?
Knowing its initial position.
Huh? You just measure, okay, x coordinate and the time coordinate at which this happened. Is it? Let's say it exploded. Huh? समझ you will just measure the time. Now, what could be a proper way to define this thing? You look at it, okay? After looking at it, what happened? So actually, you are sending the light signal to this very object, and the light signal gets reflected back to you. Is it? This is how you are actually measuring its coordinates. अगर तो ये आपको पूछो कि तो ये को measure coordinates करे? No. What you have to do? You send your signal from your eyes to this thing, and the signal gets reflected to your eyes, and then you watch actually this very event. Clear? And in this way, you are actually assigning the coordinates of this very object. Clear? So this is in the stationary case. Now let's say this is moving. What you will do? So let's say this wants to assign coordinates to you. Clear? What this will do? So this person will send a signal. Okay? Let's say at some point here, it will send a signal and then receive it back, because it is moving. After some time, it will receive it back. Clear? The signal that gets reflected by this thing. In this way, this person will assign the coordinates to that very point. Clear? समझ आया? So a proper way to do it. So you send a, let's say this is moving along a certain trajectory. It will send a signal to this very point P. Clear? समझ आया? Now, because it is moving, so this will send it back. So let's say it reaches to point. Okay? Now tell me the amount of distance that the signal travels from this point to point P. Okay, so let's call this as point A. Okay, so this distance is same as this distance, because speed of light is invariant. Clear? It's a fixed quantity. Eh? So that means amount of time it takes from A to P is same as what? P to B. Clear? Or other words, this distance is same as this very distance. Now tell me how much time has, let's say if this is some TA, he sent a signal at time TA and it is received back at time TB. Okay, so how much time duration has happened for receiving the signal? TB minus TA. The signal was in flight for this much of time. Clear? Yes. Okay, now can anybody tell me what could be the coordinates of this object? Let's take the time coordinate for the time being. Okay, tell me what is how much this distance is? C times some t. Clear? समझो, let's call this some TA. So what this will be? So T, okay, so this is the amount of time. TA, let's say amount of time. TB, let's say the amount of time. Clear? So this is the amount of distance. Can anybody assign the coordinates to this point? All the sides are given. Can anybody tell me what could be the coordinates of this P? Let's take the time coordinate first. Okay, I will give a hint. Let's assume this point P is at the midpoint. It has to be. It has to be at the midpoint. Because the signal, you send a signal and then receive back. Distance traveled is the same. Yes, what should be the time coordinate? Think. Half of the difference between the times. Clear? Good. So the time here I can write half of TA minus TB. Good. So what should be now the x coordinate? By midpoint formula? Simply the average of the distances. Clear? So what that will be? Half of C times TA plus. Clear? So that means this is the coordinate. These are the coordinates given to point P by the observer which is moving along this trajectory. Samajh? So, but what I have observed, how I have put a kind of observer which is moving with a uniform velocity. Clear? An observer can be moving along this kind of trajectory, along an arbitrary trajectory. Clear? How he will assign? So he will, okay, a general way to do it, to use the same kind of coordinates, because, okay, you can put any kind of factors here, one whatsoever. I mean, you can put any arbitrary factors. But okay, what I am saying, let's say this is the event P. Okay, so you use the same kind of things, whatsoever you are having, wherever this point P is. So they are actually the most general way of assigning the coordinates to the point P. Because let's say if this, now this, okay, why they have to be very general? Now if this observer moves along this straight line, clear? So the coordinate should reduce to this very point. So that's why we want, okay, so we keep them to be very general. Whether the observer is moving along an arbitrary trajectory or along a straight line. Got it? Okay, now tell me what are the, okay, so if proper time of this is tau A here and it is, okay, tau B for this very observer. Clear? How I can specify now the coordinates of the point A and coordinates of the point B of this moving observer? How I can do it? I must know the trajectory of this very observer. So the coordinates I can only get if I know the trajectory of the observer. If I don't know the trajectory of the observer, I cannot know the coordinates. I should know at least along which path the observer moves. So how I can do? I will make a parameterized definition of the trajectory of this very observer. Let's say what I mean by that. Since this trajectory is specified by some x and p, let's see. Okay? So how I can specify now the trajectory? You can call, let's say, some x is some f1 of tau, the function of what? The proper time, and t you can say, let's say, f0 of tau. So is this a parametric equation that will specify me the trajectory? Okay, think of this, okay, the circle what I have shown earlier. So how I define it? So x is equal to a cosine of theta. You can say x is equal to f1 of theta and y is equal to f2 of theta. Clear? And theta is the parameter. And you specify the functions f1 and f2 to be cos theta and sin theta. If I know now the trajectory, that means I know the f1 and f0. Clear? So if I know now f1 and f0, I will make an input of time t. Let's say at this very point, I can figure out what is the coordinate at a. Similarly, if I know, okay, time here, the proper time at point A, I can put it, plug it in here, knowing the function f0. So So I will get the time t here. समझ रहे हो? I can specify the times of, the coordinates of this point A and coordinates of this point B, knowing the trajectory of the particle or knowing these parametric functions. समझ रहे हो? So this is a way to understand the coordinate transformation between the two observers. Have you got the idea? Let's do it. Okay. If you have any further questions, just tell me. Okay, so let's take this trajectory. So let's take this arbitrary trajectory. So you are okay. So this trajectory is specified by. I will take a trajectory or the word line specified by. Let's use the word line specified by. Okay. So for the moving observer, so this is for the moving observer. For moving observer. Observer, that is our K frame, K prime frame. समझ आओ? Okay. So I will write it as something F1 of tau and P. By the way, don't confuse them with the coordinate times. समझ आओ? So when I will say it's a coordinate time, then it's a coordinate. Don't confuse it. What? So it will simply give me the x coordinate. So let's write. So you can put anything. So capital X and capital T. But we will reserve this capital X and capital T for later analysis. So this trajectory is specified by these functions f1 of tau and f0 of tau. It will specify means this curve. Clear? Let's take this point P. Okay. So I should say for the time being. So let me send a signal here. Then we'll use the proper notation. And is received here. ENP. Clear? So now tell me. So I can write now P prime. Since I am in the which observer wants to assign the coordinates to the point P? An observer moving along this trajectory. That's our K prime frame. Okay. So I can say. So T prime, I can write as T. The coordinates assigned. So coordinates assigned by observer K prime. It will be something TA minus TB. Sorry, it will be something TB minus TA. Difference of time is TB is higher. And what will be X? C times TA plus TA, because it is the average of the distance. Okay? Okay, so now light signal is traveling back and forth. So it is the same thing I am doing the analysis. Clear? Okay, so now tell me, you are having this as a light signal. Clear? So let's call the coordinates here. So it is some CT and X. Let me call these as X0 and T0 kind of thing. So this is X0 and T0. Let's not confuse them with what? I mean the coordinates. Now you are having a light signal. What is the velocity of the light signal? It is the C. It is fixed. Clear? Now tell me what is the equation of this? It is a straight line then. The light travels in the straight line. Now with respect to, if I orient a coordinate system here, let's see. This is X and T. Clear? So what should be the orientation of this line with respect to T or X? So that the value should be C. What should be the orientation? What is the angle subtended by this angle, this line with x, 45 degree, because light travels with the velocity. Okay, so at a velocity of c, and it is only possible if this line subtends an angle 45 degree with this x-axis or time axis. Clear? So it passes through the origin, you can say. Samajh aaya? Okay, good. Now what is the this thing? So this also a light signal. Samajh aaya? Let's say if you are having a slope here positive, what should be the slope here? Negative. Now tell me, what is the equation of the straight line? Huh? So difference of the coordinates. Samajh aaya? So I can write now the equation of this AP. Okay. So let's write the equation of AP. So it will be something x minus xa. So you can write xa is the point here. Eh? So that we need to figure out xa and ta, and here what it is, xb. Because the signal goes from where? Point A. So it will be some c t minus ta, and similarly you can be having x minus xb. So that is something c of tb minus t. So that's minus times c of t minus. So all, okay, so this set of equations is 1, this set of equations is 2. Clear? Any problem? Just try to understand it. Huh? I will provide you the notes. Notes details are given. Huh? Okay. Now let's write then this x minus from here. So let's write. It says x minus ct is equal to. Now tell me. So you take xa here. So it is xa cta, and similarly you are having x plus ct is equal to xb minus, or sorry, plus ctb. Equation third. Okay? Any problem? Just what I have written. X minus ct. X and ct are the coordinates here. Clear? So xa and cta are the coordinates here. Clear? Samajh aaya? So which coordinates are known to me? Here. Because the curve is known to me. Huh? Samajh aaya? Now let's figure out what is the curve. X naught is equal to f1 of tau. Got it? Samajh aaya? So in other words, I can write now, let's figure out the points. Which points? xa and ta. Samajh aaya? Now tell me what are the coordinates of point A in terms of these functions f1 and f0. Look here. So xa is the coordinate here. But where from I can get it? If I know the curve. Samajh aaya? Or if I know the function of the curve, which represents the curve. You plug in what? The value of, let's say, time or whatsoever there, you can get in terms of the functions. Samajh aaya? You get the value of xa and ta. So what is xa? So tell me from parametric form of the equations, xa will be something f1 of tau a. The proper time specified where? At point A. What will be now ta? f0 of tau. Similarly, you will be having xb and, okay, so xb will be f1 of tb, tau b, and tb will be simply f0 of tau. Samajh aaya? Samajh aaya? Okay, so now let's substitute in equation third. Okay, so from equation third, so what you get? You get actually x minus ct is equal to f1 of tau a minus c times f0 of tau b. Clear? Similarly, you can get x plus ct as f1 of tau b plus c times f0 of tau b. Yes? Any problem? Now specify what is tau A and tau B. You can write, because Ta and Tb, they are the values of the proper time where at the points A and B. Clear? I can specify that proper time in terms of T prime and X prime. You can solve here. Let's figure out what is Ta. So let's take subtract the two. So it will be So it will be something T prime minus X prime by C. समझ Shivan? So from equation 1, you can write this tau A and tau B. So we get x minus Ct is equal to F1 of, okay, so T prime minus X prime by C plus, minus C times F naught of T prime, because tau is same at both the functions. Similarly, you can get x plus Ct is equal to F1 of T prime plus X prime by C plus C times F naught of T prime plus. Now look here. So if I know F1 and F naught, so I get what? The relation between x's and x primes. Unprimed and primed coordinates get related through the functions F naught and. So this is the most general coordinate transformation between two frames of reference. So whether they are moving with the linear, they are moving with a uniform acceleration, or they are moving with the uniform velocity. Clear? So these formulas will be used later on in when we will do the equivalence principle. समझ आओ? If you have any problem, any doubt, any misunderstanding somewhere in these equations, just tell me. Okay? So now let's take a special case that will yield our Lorentz transformation. Are you tired? Okay? So I will take this K prime frame moving with uniform velocity. Uniform velocity v with respect to P. K means with respect to that point P. Clear? So समझ आओ? This is our K prime frame of reference, and you can call this as what? K frame of reference. So समझ आओ? Let's try to figure out the relation between the coordinates. Okay, in this very simplest of examples. Now, when you are having this particle is moving along its world line with a uniform velocity v, what is the how I define the trajectory? Okay, so I define the trajectory like this thing: x is equal to vt. Sorry, I have given the f1 of tau, and then we wrote x naught t naught f naught of tau. Clear? Suppose if a particle moves with a velocity v, so how I specify the coordinate? Just multiply velocity and time. Clear? So in other words, the trajectory in this very case, so it will be specified by x naught is equal to v times t. समझ रहे हो? Is this true? So, and what will be this t naught? Simply t. समझ रहे हो? The time for which this particle evolves, starts, okay, the time for which the particle moves from one point to the another point. So this will be, these will be the functions that will specify my trajectory. So, think of a particle that's moving with a uniform velocity. How do you define now the x coordinate? Velocity into time. Clear? So this is the standard definition. And how I will specify the time? Just by the time. Clear? Okay? So now tell me what is our... So therefore f1 of tau will be what?
VT.
Okay, so that is Vt. Let's write t in terms of tau. Okay, so let me write it in, because I have to put it in the proper time. this t is not the proper time. Huh? So much more, let's put it in the proper time. So it will be v. What is t? So it will be tau divided by root of 1 minus v square by c square. So that's equal to gamma times v tau. So let's put this also in the proper time. What it will be? Gamma times tau. So because I have defined functions, I have to define function in terms of the proper time. Clear? That's why I am using for this t. I am converting this time in terms of the proper time. Now tell me what is our this f1 of tau? Gamma v tau. Clear? And what is f naught of tau? Gamma into tau. Okay, now what you are supplying the argument instead of tau? T prime minus x prime by c or t prime plus x prime by c. So now let's try it. So therefore I can write this x minus ct is equal to, from these equations, what is your f1? Gamma v. Okay, so what is the argument for tau? So it is t prime minus x prime by c. Then you are in minus c. F naught is what? Gamma times tau. What is the argument for tau? T prime minus x prime by. Let's work it a little bit. You can take gamma. Okay, so there is a gamma. Yes, there is a gamma. That gamma times tau. Huh? So it's like this. Gamma is outside. Tau is c times this thing. Sorry, c is here. I'm sorry. C is here. Huh? It is same thing. C is there. Huh? Sitting in front of f naught. So you take gamma out. So what remains? Now let's take for the coordinates of the t prime. Huh? You are having minus c here. Let's take it like this. Huh? Okay, so minus ct. Okay, let's say plus v t prime. Then you are having x prime. Okay, so minus x prime. What you are having there? So if I take x prime out, so what you are having here? V by c. Okay, so it is something v by c, and it will be here plus 1. Plus 1 or minus 1?
Minus 1.
Hilal? Is it true? Okay, so no. So it should be plus then. So minus and minus is plus. You are taking minus out. Okay, good. So what you get? So it is 1 divided by root of v 1 minus v square by c square into x prime minus ct. You can take out ct prime like this thing. What remains here? It is 1 minus v by c. Clear? So now root of it is 1 minus v square by c square. You can put what? 1 minus v by c into 1 plus v by c. 1 minus v by c will cancel out with this thing with a root. So it will be something root of 1 minus v by c divided by 1 plus v by c into x prime minus ct prime. Call, let's say this as first. Similarly, you can take now x plus ct also. X plus ct you can take as, so you are having gamma times v. Okay, f1, it is now t prime plus x prime by c. So it will be simply t prime x prime by c. Then you are having plus c times gamma. For tau you put t prime plus x prime by. Once you evaluate this thing, it will be 1 plus v by c divided by 1 minus v by c into x prime plus. Clear? Just a little bit algebra. It's not a hectic job. So now let's solve for x prime and t prime, or let's solve for x and t. Clear? So what you will get? Okay, solving these for x and t. Okay, solving equation is 1 and 2 for x and ct. You get x is equal to x prime plus pt prime. and you get actually gamma into x prime t prime plus v by c square. Unprimed are related to the primed by this. Is this a Lorentz transformation? Okay, consistency requires. So you can convert them. Consistency requires. You can write t prime. So x prime is equal to gamma into x minus vt, and t prime is equal to gamma into t minus v by c square. So that means you require actually v goes to minus v. It's not as simple as that. You are taking v to minus v, so you can put it in the matrix form. Xt is equal to a 2 by 2 matrix into x prime t prime. Clear? So then invert that matrix. That will appear as you have to change from v to minus v. Clear? Samajh? Now let's look at this formula for t prime. Oh, now I go. This is not t prime here. Okay, it is t. Now let's look at this very formula. What this t prime is? T prime is actually the time shown by the moving clock. What is that? It is proper time. Now you are having the coordinate time related to the proper time. So this amount of this gamma t prime gives you actually the time dilation between the clocks. Okay. Now there is an additional factor. Remember the amount of non-synchronicity or the amount of non-simultaneity we have calculated? What was that? Gamma times v by c square into x. Clear? Length. You remember? So this is the amount of non-simultaneity. Samajh aaya? Clear? So now look at this. Why this is simple? This coordinate. Now if you see this kind of factor or this x minus vt factor, what you know. This is the same, forget about this gamma for the time being. This is the same thing what you observe in the Newtonian mechanics. If you have the Galilean relativity, you observe the same kind of factor, okay? But now there is only what is happening. A gamma is appearing here, okay? This is due to what we call a length contraction, okay? And you see now space and time get actually mixed. The effects are interrelated. It is because of this space and time are not the separate entities. They are one and the same. Or they are actually interrelated through this kind of transformation, okay? And because of this interrelation, you are actually getting these kind of coordinate effects, time dilation or the length contraction. Samajh aaya? And you can see actually the relativity is absolute kind of thing. Suppose you are having in this way, so you are taking this t prime to be what? What t prime is? It is the time shown by the clock that's moving with velocity v, and here it is what? The proper time shown by the clock, and this is your coordinate time. Now let's look at this thing. Now you are having the frame moving with the velocity minus v, is it? So it means this t is what? The time shown, proper time shown by the clock which is moving with the minus velocity. That is the same thing, the clock which you are observing at rest. I mean you are moving with velocity v and you have your clock, but the observer which you are seeing, okay? So that moves with you with respect to with a velocity negative. Clear? So this will show you the proper time for that clock. Clear? And then this t prime will be coordinate time. Clear? So is this now the they are actually it is truly relative. There is a symmetry between the events. So samajh aaya? Okay.